Hi everyone, can you all hear me? Okay, great. And can you all also see the whiteboard? Okay. So if there are any issues with the audio or video, please check your audio and video settings because it looks like it's all good from our end. So in that case, we can quickly get started. Yeah, hi. So I think many of you might be meeting me for the first time. So I think I'll quickly introduce myself shortly. So I'm Vivek, one of the co-founders at Programming Pathshala, apart from Bharat and Anu. And yeah, I take care of academics and technology part over here. So Bharat told me that you guys have been learning with him and you guys have been learning with him very, very well. So I was very eager to kind of meet you all. Today, however, we'll be starting a new topic. And this topic has dependency on whatever you have learned so far. So, yeah, so let's get started. So as of now, can somebody quickly type it in the chat box, what topics or concepts you have learned so far? Let's quickly type it, just for me to be aware of it. Okay, recursion. Yeah. Okay, cool. So you guys have learned recursion, and I believe you might have solved some problems on top of that. And the nature of problems that you would be solving, your input would be an array or a vector or a list, something like that. Okay. So now we are going to talk about a completely different data structure. So why do different data structures exist? Let us understand this thing first. Let's say somebody tells you that, hey, I'm going to give you 100 numbers, 100 integers, and those 100 integers have no relations with each other, right? Then it does not really matter how you structure their storage. I mean, if you have been given, let's say, some integers like 5, 1, 2, 3, 0, it does not really matter how you store them. If you want, you can store them in an array. If you want, you can store them in any other data structure of your choice, right? But sometimes what happens is that the data which you have been given, that data has strong relations with one another. And when it has strong relations with one another, then just storing it in a simple linear array or a vector or a list would not make sense. When I say would not make sense, what I'm trying to say is there will be information loss. What I mean by information loss is, let's take a very quick example. So let's say there is a company, and in every company, you know, there is a hierarchy of employees. Okay, so the first person is, let's say, CEO, and let's say under CEO you have got CTO, and then CFO, and then COO, and then again under CTO you have got a vice president of engineering, VP1, VP2, and under these vice presidents you have again got, let's say, directors, director 1, director 2, and here you have got, let's say, director 3. Again under this director 1, let's say you have got manager 1, manager 2, here you have got a manager 3, here you have got a manager 4, and now again under them there can be some tech leads, and under them there can be some SDs, and under them there can be some interns. So there is a huge structure like that, correct? Now for every employee, let's say there is some kind of ID or some kind of tag. So let's say the ID of CEO is CEO. This guy is VP1, this guy is VP2, this guy is director 3. Now, if you want to store this data and if you want to just store it in a linear array, then you can say, okay, I can just take a linear array, and the first element of that array can be a string CEO, the second element can be CTO, and the third element can be something else, something else, something else. So if you store the data like that, what you will lose is you will lose the parent-child relationship. What I mean by parent-child relationship is, here you can say that, hey, CEO is the parent of CTO, CFO, and COO. CTO is the parent of VP1, VP2. So if you're just storing it in an array, you will not be able to make out that who was the parent of which all things, right? So it is important to store such kind of data in a different kind of structure. And this gives rise to some very well-known hierarchical data structures. Okay. Now, there are varieties of hierarchical data structures, but the most basic of them, which we'll be learning today, is called as trees. Okay. So data structures exist because the problems exist. Like one problem over here is certain data can be hierarchical in nature. Whenever a data is hierarchical in nature, the best way to store that is in form of a tree, because when you store that in form of a tree, you preserve the parent-child relationships. Does it make sense to everyone? Yes or no? Yeah. Okay. One of you is asking why we can't use 2D array for storing. You answer me how 2D array can solve your problem. How is 2D array different from an array of arrays? Just think about that. That's no different. You have a 2D array, which you are visualizing like that. Where will you store this root? If you are saying you will store your root here in the middle, I would say does not make sense. In that case, let's say you store your CTO here. Let's say you store VP1 here. Where will you store this D1? I mean, you will have no clue how big in terms of dimensions do you need your 2D array to be, right? So in case of a tree, what happens is that the structure is not really fixed. You do not really know that how many children COO will have and how many grandchildren it will have. So whenever you are planning to use array or 2D array or anything like that, which has a fixed storage, it just does not make sense. Yeah. Correct. Okay. One of you has another question. Why can't we use linked list for that? You obviously can't use linked list for that because those of you who know about linked list, you would know that in linked list, what happens is that if you have got a node, let's say that node is CEO, then it can point to only one another node. It cannot point to 2 or 3 other different nodes, correct? So you can say it that tree is a special kind of linked list, which is not linear, rather it is hierarchical. And because it is hierarchical, in hierarchy, there can be multiple forks. So from a node, there can be multiple pointers instead of just one pointer. Yeah. Okay, cool. Now, before we just move on and solve some quick and easy problems on trees, I would want you guys to use your brains and tell me, can you give me some other day-to-day practical example of hierarchical data structure? I have given you an example, which is employee hierarchy, but apart from that, is there another example which you can give me? File system is awesome. Great. So file system is a great example. So if you guys have your computers in front of you, you can easily see that in most of the computers, you have got, let's say, multiple drives. So let's say first you have a My Computer high level drive, and within it, let's say you have C, you have drive D, you have drive E. Now within every drive, there can be multiple folders. So let's say this is folder number 1. This is folder number 2. This is folder number 3. Now, again, within these folders, you can have files. Let's say there is a file f.txt, another file let's say bat. There can be multiple files within it. And within a folder, there can be some other subfolders also. So who knows, within folder 2, you again have folder 4 and folder 5. That's how it goes, right? So there are ample of examples like that. And because of that, things like trees exist. Now, why we are learning trees after recursion? That is another very fundamental question which you should ask yourself. Or more broadly, I would say, why do we learn recursion? So I'll tell you, we learn recursion because most of the data structures, or I would say all the data structures that we have, they are recursive in nature. So here I am saying data structures are recursive in nature. What I mean by data structures are recursive in nature, let us understand that first. Let us take the simplest data structure, which is an array. Okay, what does recursion do? Recursion solves a very small part of a big problem and then delegates the remaining part to the next call. That is what it does. And that next call is the similar kind of problem only. If you look at an array, I can say this array can be thought of as, let's split its one element and let's preserve the remaining part. So I can say it can be split into an element, a single element, and a remaining part, and this remaining part is again an array. The only difference is that this is an array of size n and this is an array of size n minus 1. Now again, this can be split into an element and a remaining part, which is again going to be an array, just that it will be of smaller size. So no matter what data structure you have, you can use recursion on it. Why? Because you can always take away something from it, and then whatever remains is the same thing with a smaller size. Do you get my point on this? Yes or no? Right? The same is true with trees as well. So let's say you have got a very simple tree which looks like this. Yeah. In this tree also, you can say, what I can do is I can take away this root. So let's say this is our root. Let me take it away. And what remains is two smaller subtrees. Correct? So if you have been given a big tree, which was like that, then you can say this is a combination of a root, which you can say is this, and then there is a left subtree, and then there is a right subtree. These three things make up for a complete tree. So what do you see? Again, this tree is a recursive data structure. So whenever you are solving any question on top of a tree, you have to visualize a tree like that. You do not have to visualize a tree as so many things which are jam-packed. Just visualize it as if there is a root. So do something with the root, and then do something separately with the left subtree and with the right subtree. Because if your algorithm can deal with left subtree and right subtree properly, then it can deal with the big entire tree also, because the entire big tree is also a tree. The only thing that differs is size. Okay, cool. So from here, I want you to understand it very clearly that whatever you have learned in recursion will be directly applicable in case of the trees. We will solve some problems, quite a lot of problems, where there'll be some use of things like base cases and recurrence relations that you might have learned in your recursion classes. And we'll see how it goes. If you have any questions based on whatever I have said so far, feel free to ask. Okay, cool. So the first question that you should be asking yourself is that, okay, how to implement this tree? How to not implement, I would say how to represent this tree. So when you look at a tree, let's say you have got in tree you store data, and that data could be anything. So let's say you want to store integers, sometimes you want to store characters or strings, that's up to you. So let's say you have a very simple tree like 5, 4, 7, 3, 2, 1, 9, something like that. And it can go on and on. It can go below as well. So here, everything that you see, 5 or 7 or 3 or anything else, that is called as a node. Okay. Now, what are the things which are present in a node according to you? Apart from this data 5 or this data 3, is there something else which is a property of node? Address, child links. Okay. Cool. So that is totally right, because these things that you are seeing, which are coming out like that, they are part of this node only. So I can say, if I define the structure of a node, so those of you who are comfortable with C, you can use struct. You might have learned it. That's a basic programming construct. Or you can use class if you are comfortable with C++, Java, or any other language. So let's say you have got struct node. Now inside this, it is made up of some data. And now that data will be of some type. Here it is an integer. Okay. And apart from that, there will be different pointers. These pointers will be storing the addresses, pointers or references, depending on your language type. Okay. So basically, these things will be storing the address of the child nodes. So think of it in this way. If I try to draw it more cleanly, I can say this is a node, and here some data is present, and here in this compartment, the addresses of its children will be present. I do not know how many children it has. This node can have 3 children directly attached to it, or 1 child, or no child, or 100 child. That's totally up to it. So let's say there is some child over here, and let's say its memory location in computer is memory location 1000. Then here you will store that 1000. And by that, once you have stored that 1000, then you know where this child is, where this rightmost child is. So it acts like a pointer. Similarly, let's say the next child is present at memory location 1009. Then here you store this 1009, and that way you point to this. Similarly, for another child, memory location is something else. You store that over here, and then you point to this. Okay. So you need to have as many pointers over here as many children you are pointing to. Okay. Now what we'll do is, for convenience sake, we'll start with the simplest of the tree, and that simplest of the tree is called as a binary tree. Because there is no point discussing linear tree. When you say linear tree, that means you are saying that a node has only 1 child, and now that node again has only 1 child. So that is like a linear thing. That is not a hierarchical. So the simplest form of tree that we will talk about is a binary tree. The meaning of binary tree is bi means 2. So it has, so basically I can say every node has at max 2 children. At max 2 children. Here the word at max is very important, because certain people feel that, hey, every node should have 2 child each. No, a node can have 1 child also, and a node can have no child also. That's totally okay. That being said, is it correct to say that this is a binary tree? Yes or no? Yeah, it is totally correct, because when you look at the nodes, this node has 2 children. That is totally okay. This node has no child. That is also okay. So each node has at max 2 child only. That's it. Cool. Now moving ahead, I can say here, I can basically categorize these nodes into, I would say, 3 broad categories. The first category is root. So this is called as root. So root is that which does not have any parent. As simple as that. Okay. And now these things are called as leaves. So leaves are those which do not have any children, 0 child. And then these are your intermediate nodes. So your intermediate nodes, they can have 1 child, like this guy has only 1 child, and sometimes they can have 2 children also. That's totally up to them. So these are the broad categories. And what I would like to tell you is, whatever code you are writing for solving a problem on trees, there, if you have to think of edge cases, you should always think about root and leaves, because most of the times people mess up dealing with roots and leaves. So whenever you see that your code is dealing with a leaf, you have to be careful. Same is the case with root. For intermediate nodes, generally people do not make mistake, and you will realize that in the time to come when you actually write the code. Okay, so now that we are dealing with binary trees only, so I can say that, hey, in binary tree, let's say if we are storing integers, then here there will be some data. And then here I'll have M1 and M2. M1 is the memory location of this node, where I can have some other data. So let's say the data stored over here is 9. And then the data stored over here is, let's say, 10. Okay. And then this again has, let's say, M3 and M4, which is used to point to some other, nodes. What is the address of this? The address of this is M1. The address of this node is M1. That is the reason this M1 is stored over here. Similarly, let's say there is some other node over here, has value 15 in it. So, and let's say the address of this is M2. That is the reason this M2 is present over here. Let's say this is a leaf. If it is a leaf, then here also you will have null, and here also you will have null. So if you take a look at, let's say, this node, its left and right, both pointers are null, because it does not have any child associated with it. Okay, that's how it goes on. So let's say you have another node called 11 over here, which is again a leaf. null, null. And of course, its memory location would have been M3. That is the reason it's stored here. Okay, now you must be thinking one thing, that for every node that we have, its address is stored in its parent. Its address is stored in its parent. But how about the address of this? The address of this also needs to be stored somewhere. Because if you do not know the address of this, then you will not be able to traverse across the binary tree that you have. So the address of this, if that is M, that needs to be stored in a special variable. Let's call that root. Root equals to M. Why the address of this needs to be stored in a special variable is because, think of it in this manner. You have a big tree, and if you just have access to M1, there is no way you can go back from M1 to this M. Why? Because these edges that you can see are directed edges. Directed edges means you can, if you can go from here to here, then you cannot come back from here to here, because there is no way at this node you would get to know about this M1. But here you would get to know about M3, and you can go to M3. So you can come down, but you cannot go up. That is a big trouble which is associated with this kind of representation of tree, where we use pointers to point to the different children. Is that making sense to everyone? Yes or no? Yeah. Okay, great. Cool. So so now that we know this particular thing, and we are talking only about binary trees for simplicity, I can say that, okay, the left child or right child, so I'll refer to them as left child and right child. At the end of the day, they are nodes only, and their address can be stored in the corresponding pointer. So you can store them in struct node star. This is the data type of the address of this thing, and you can call that as left. And similarly, you will have struct node star right. If you are using C++ as your language, then this struct keyword over here could be redundant. You can check your version and types. You can omit that. That's up to you. Cool. So this is the the actual structure of the nodes that we'll be using in general. Now let's move on. So now let me ask you a very basic question here. So when you talk about a tree, then there is a very important property of tree that you should always remember. Let's say you have got 2, 7, 1, 3, 5. Yes. Is this a tree? Yes or no? Why it's not a tree? How is this structure different from whatever I have drawn so far? Cycle or two parents. Very good. So when you look at this thing, it has got two parents, or in other words, you can say there is a cycle, right? Tree is an acyclic graph. Keep it in your mind. In tree, there cannot be any cycle at all. If cycle is present, then it's no longer a tree. You can call it a graph, because in graph you can have cycle, you cannot have cycle. So graph is a superset of trees. Okay, every tree is a graph, but the reverse is not true. Now this is a very important point, and based on that I'll ask you a question. Let's say there are n nodes, like here 1 2 3 4 5 nodes are there. Then if there are n nodes, then how many edges would be there? Can you think of that? N minus 1, right? You can see that is happening here also. Like here, the number of nodes is 1 2 3 4 5, and the number of edges is 1 2 3 4 edges. But it's not a mere I would say coincidence. It can be very easily seen why this is the case. So tell me, if you have a tree which just has one node, and that node is, let's say, 2, it just has a root and it does not have anything else, then I can say here the number of nodes is 1 and number of edges is 0. Now let's say you want to introduce an edge. can you introduce that edge over here without introducing a new node? I'll repeat my question. Can you introduce an edge over here without introducing a new node? The answer is no. Some of you might be saying, hey, how about doing like this? I would say if you do like this, if you make a pointer point to this thing only, then that will be case of a cycle, which is not allowed. So if I want to introduce a new edge, I need a new node. Let's call that 3. And in this situation, what has happened? So see what I'm saying. If you want to introduce an edge, that means if you want to do a +1 here, you want to do a +1 here also. For every new edge that you want to introduce a new node. And now I'll move on. Now, let's say you want to introduce one more new edge over here. Can you introduce a new edge without introducing a new node again in this existing tree? 2 of you are saying yes. My question was, can you introduce a new edge without introducing a new node? Let us try doing that. You can say that, hey, how about this edge? Again, there is a cycle. That is not allowed. Any other option that you have? 3 to 3, again cycle. 2 to 2, again cycle. You can't do that. So if you want to introduce a new edge, you need to have a new node. So that new node could be 4. And you can either directly link this 2 to 4, or you can link this 3 to 4. That is up to you. That is up to you. The structure of the result tree will be different. But the only point is that if you have introduced this, you introduced that also. Similarly, again, if you want to introduce a new edge, you have to introduce a new node, because if let's say you introduce this edge, there will be a cycle. So if you want to prevent that cycle and yet introduce a new edge, you have to have a new node. So this 5 could have been brought here also. That is up to you. And this 5 could have been brought there also. That's up to you. So what is happening here is that the initial difference between n and e was 1. And now when you are doing a +1 here, you are doing a +1 here also. When you're doing a +1 here, you are doing a +1 here also. So the difference between node and edge will be of 1 unit. And it will continue to be like that. Because of this reason, I can say that number of edges will be equals to n minus 1, where n is the number of nodes. Does that make sense to everyone? Yes or no? Right? So just keep this thing very clearly in your mind. This is a very important property of trees. And because of this property, there are no cycles. Okay, let me ask you another question. Let's say there is a big tree like that. I'm going to ask you a very simple question. How many paths are there from 9 to 1? You are at this city right now and you want to go to this city. How many paths do you have leading you from this to that? There'll be only one path. If you want to go from here to here, of course, how you can travel? You can travel via edges. Just imagine that these edges are like roads which are connecting different cities. So you can go from here to here, here to here, here to here, and here to here. There is no other way. Find me anyway. There is no other way. Why? Why does this happen? Because there are no cycles. Because there are no cycles. And let me tell you why this is a consequence of no cycles. Because if let's say there are 2 nodes, let's call them N1 and N2. These nodes are part of a very big tree. I have not drawn the entire tree. Now let's say there is some kind of path from here to here. And then you are saying that, hey, there is yet another path also from here to here. That means there is a cycle. There are 2 cities. There is one road from N1 to N2, and there is another road also from N1 to N2. That means there will be a cycle. And because there are no cycles, it means there will be one and only one unique path between any 2 pair of nodes that you choose. Does that make sense to everyone? Yes or no? Okay, cool. Now one of you is saying how to detect the number of paths. You have to define what is the meaning of your path. We'll come to questions like that. Don't worry. Cool. So these were some very, very basic information that I wanted to share about trees. Now we can just move on. Okay, so let's say there is a tree. This is your root. Okay. Such kind of a tree is also called as a perfect tree. Of course, it has a different names in different places. But why I'm calling it a perfect tree is because you can see that it is a perfect triangle. So there is a root and it has two child. Again, there is a root. Sorry, there is a node. It has two child. Again, there is a node that has two child. So the property of this tree is that all these levels that you can see are completely full. Level 1 is full, level 2 is full, level 3, level 4, all these levels are full. And in the last level, all the leaves are present. Okay. Okay. So can you count the number of levels? How many levels are there in this tree? Yeah. Okay. So there are 4 levels. So this is your level 1, level 2, level 3, level 4. Now, if let's say you have a perfect tree where the number of levels is, let's say, h, then how many nodes will be there in that tree? Very simple question. What is the total number of nodes in a perfect tree? Let me write perfect tree where number of levels is h. Okay, one of you has a question. If you give 3 childs means to each parent, I did not get your question. Currently, anyways, we are talking about a binary tree, and in what context you are asking, I did not get that. Maybe you would want to rephrase. Yeah, in the meantime, what will be the number of nodes? Okay, so you guys are saying 2 raised to power n minus 1. Do you see there is no n? From where you are bringing n? I said number of levels is h, and then I'm asking number of nodes. So your answer should be in terms of h, right? Okay, many of you are saying 2 raised to power h minus 1, and some of you are saying different. So let's take a look at that. See, here there will be only one root, right? And because the tree is perfect, at next level there will be 2 children of it. At the next level, 4. At the next level, 8. So in general, I can say if there are h levels, here I'll have 1. Here, this 1 is also 2 power 0. And then 2 power 1 nodes here. And then 2 power 2 nodes here. So on and on, 2 power h minus 1 nodes at the last level. And now if you take a look at this thing, 2 power 0 plus 2 power 1 plus 2 power 2 till 2 power h minus 1, then this is a very special kind of series. This is a, which kind of series? GP, geometric progression. Now, do you guys know the sum of GP? You can take a look at that. It's a very basic maths. It is A, where A is the first term, into R, where R is the common ratio raised to n minus 1 upon R minus 1. R is the common ratio. The common ratio here is 2 because every next term is 2 times the previous term. The first term here is 1 and the R is 2. The number of terms from 0 to h minus 1 will be h minus 1 upon 2 minus 1. So this 1 and 1 is gone. So it will be 2 raised to power h minus 1. So the total number of nodes is 2 raised to power h minus 1, which is also order of 2 raised to power h. So I can say as the height of the tree increases, this h is height. As the height of the tree increases, and if it's a perfect tree, then the number of nodes will exponentially increase, because in every below level, the number of nodes will become twice of the previous one. So it's just like a binary fission reaction that is happening. It can be modeled as a tree. Or does it make sense to everyone that how is it 2 raised to power h minus 1? Yeah. Okay. Similarly, so if let's say I call this thing n, because n is the number of nodes. Now, if somebody asks you reverse question that, hey, if there are n nodes, then what will be the height? If the tree is perfect. If there are n nodes, then what will be the height if the tree is perfect? Can you think about that? It will be log of n base 2. Why log of n base 2? Because if you take log of this thing, see, this thing is almost 2 power h. So if you are taking log of 2 power h base 2, you will get h, which is the height. So if there are n nodes and if the tree is perfect, then the height of that will be log of n base 2. Okay, now let's come to some worst cases. I told you that in a binary tree, a node can have at max 2 child. So the worst case could be that every node has 1 child only, just like a linked list. So in that case, what will happen? You have a root, it has a child, 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 and so on and on and on. Such kind of a tree is also called as a skewed tree. Skewed in one direction. So it goes like right, 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 or it could go like left, 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 left. Okay. In this case, log of n plus 1, again, like that does not make sense what you are asking, because when you are doing asymptotic analysis, how is log of n different from log of n plus 1? There is no difference. They are almost the same. Okay. So when you learn about time and space complexity broadly, you will learn that. But answer me this thing. If there are n nodes and the tree is skewed, then what will be the height of such a tree? It'll be n, because you can say that each level has only one child. Cool. Yeah. Now let's just move on and come to the practical things. The kind of questions that are asked in interviews, will directly attack those questions. So see, once you have defined this structure for yourself, then you can create a node, you can delete a node, you can add a children to a node. Those can just be done by using some basic programming constructs. So depending on what language you use, you can use the desired construct. So if let's say you are a C programmer, you might have heard of something called as malloc. So using malloc keyword, you can dynamically create a new node. What I mean by dynamically create is during the runtime. So you have a tree that is given to you. When your code has compiled, then there is a basic tree. And now in the runtime, you want to create a new memory and you want to add that as a left child of some node, you can do that by using maybe malloc keyword. So how malloc keyword works is you do malloc and you define how much size you need. Okay. So let's say you want one node. So the size of one node you can get by size of operator. And here you can mention struct node star. Okay. And then you can just typecast it. You can typecast it to struct node star. And then this typecasting is important because whenever you call malloc on something, this is the size, this is the amount of space that you need. Whenever you call malloc on something, then it returns you a generic pointer. Now you need to typecast it that, hey, this pointer is actually of the type struct node. And then you can just store it in some struct node star p. And once you have this p, then you can use arrow operators and you can assign something to it. So you can do p arrow data equals to 10, p arrow left equals to null, and you can also say p arrow right also equals to null. This simply means once you have done these things, it means you have created a node where data is 10 and its left pointer is also null, right pointer is also null. Okay. And now over the time, if you create another node, let's say p1, then you can assign this p1 as the left child of this or as the right child of this. For that, you just have to do is p arrow left equals to p1 or p arrow right equals to p1. Yeah. Does it make sense? Again, this is not a conceptual thing. This is just a language specific thing. So its understanding would vary from person to person depending on what language you use. Does that make sense? Like how you can create different nodes? Yeah. Just in case if you are a C++ or Java coder, you can just use new keywords. Do you guys know about new keywords? Ever used it? Forget about this. If you are so afraid of it because it's too long, forget about this. You can use a new keyword. You can do new of node and you can pass whatever you want. So let's say you want to create a new node that has a data 10 in it and the left and right pointer are null. You can just do this thing. And this returns you a node star p. This was for C programmers. It's good to know about keywords like malloc, right? So this thing is same as that thing. What it will do is it will create a new node for you which contains data 10 and has left and right pointers as null and null. And then later you can, again, using the same piece of code, you can create another thing. Let's say you are calling it Q. When you are calling it Q, you will get another node with value 20 in it, having null null. And now this was P, this was Q. So if you want to attach this as the left child of that, you can just do P arrow left equals to Q. That way what will happen is this will start pointing to this. And if its memory location is, let's say 1000, this 1000 will be recorded over here. So all that I'm trying to say is you can use new keyword, you can use malloc, whatever is present in your language, and you can use that to create a new node with the desired data and the desired left and right pointer. And then you can attach them using the operators like arrow operators, which are, I think, available in all the languages. In certain language, you do not have arrow operator, but you have dot operator. Like in Java, you have a dot operator. You can do P dot left equals to this, P dot right equals to that. So I would want you to do some revision today. Today, when you go back, please revise pointers and references, structures and classes, these things, because they'll be very, very handy while you actually write the code. You do not need to go in the entire depth of them, but please understand them on a very high level, like what pointers are, what these kind of operators are, what is new keyword, what is malloc keyword. And you can look at some basic programs of trees where they have been used so that you can use them very easily. No need to go in deep details, just understand how they are used. Does that make sense to everyone? Can everyone do that? Yes or no? Yeah. Okay. Great. So let's move on. This is the structure which we will fix ourselves to. Okay. And then we will solve a very basic question. See, if you have an array, then nobody is going to ask you that, hey, tell me how many elements are present in the array, because that is a nonsense question. Array has a default size. So whatever is the size, that will be the total number of elements until unless you have initialized them. But when you have a tree, then it can be a good question to ask that, hey, this is the root, and now count me the number of nodes present in this tree. So let's say you have a tree which is rooted at this node 5, and you have 6, 9, 1, 2, 3, 0, 1, 4, something like that. Somebody asks you that, hey, count the total number of nodes. How will you do that? So you cannot do this question just by using a for loop or just by using a simple traversal. In a linear data structure, what happens? You can travel from I equals to 0 to I equals to 1, I equals to 1 to I equals to 2. But in this case, that is not possible. So you will have to take refuge in recursion. Now, I told you, if you have to solve a problem of tree using recursion, then you have to break this tree into a root and a separate left subtree and a separate right subtree. You have to think like that. When you think like that, you will be able to come up with some kind of recurrence relation, what you would have learned in recursion, like how a function is dependent on other functions, and then you will be able to code it. So let me ask you, how many of you can write a program to count the number of nodes present in this tree? Okay. By the way, let me answer one question. One of you is still asking that why we can't use iteration. Let me ask you, how will you use iteration? When you use iteration or a simple for loop or something, until unless you are using some special data structure that can replace recursion, you will have a pointer here. Let's say that pointer is P. Now, from P, you can move to P left. From P left, again, you can move to P left. Now tell me one thing, all that you have done is you have come from here to here, from here to here. Is there any way to go back from here to here, here to here, and here? The answer is no, there is no way to go back. So when you are using simple iteration, moving from one place to the other, from one place to the other, then you will keep going in one direction only. And this is a tree, this is not one directional. This can be multi-directional, you understand? So you cannot just make use of something as simple as iteration. So how do we think here? So you might have learned in recursion that using recursion, you can make multiple calls, right? And those multiple calls are here for the multiple edges that are coming out from every node. So think of it in this manner. This is a tree rooted at this root R. So let's say I have a function count of R. This count of R will tell me that how many nodes are present in the tree whose root is R. Now, definition of the function is very important. It returns me the number of nodes present in the tree which is rooted at R. Then I can say this is equals to 1 plus count of the nodes which is present in left subtree, which will be rooted at root left, plus count of the nodes which is present in right tree, which will be rooted at R right. You know, this is also called as a subtree. This is also called as a subtree. The way you have a subarray, you have got subtree also. And for every tree or subtree, its representative is its root. Because you have to be at root, then only you can travel all the other nodes coming down from it. So I can say number of nodes present in this is equals to 1. Why 1? That 1 is for the contribution of this. 1 plus the number of nodes present in that, plus the number of nodes present in that. When you look at this equation is saying that if you have to find the number of nodes in the big structure, then you first have to find the number of nodes in smaller structures. You find the number of nodes in this, find the number of nodes in this, add 1 to it. That's how you get the number of nodes present in this. And what is this? This is purely a recursive equation, which you can code and get your job done. Is it making sense to everyone? Like what this equation is and why this is fundamentally correct before we code it? Okay. Now, tell me one thing. What is it which is very special about recursion? Or what is it where you miss out on edge cases in recursion? Base conditions, termination conditions. Very good. Tell me, is this thing correct for all the values of root or all the subtrees? Does it make sense? So let's say you come here, you are just talking about this much of subtree. Here, if you have to count the number of nodes and you say it will be 1 plus count of root left plus count of root right, okay, then what will happen is count of root left means you will go to null because root left is null, and count of root right would also mean that you would go to null. Now, when you are going to null, then there will be some issues. What kind of issues? Let's say you come over here and you again make this call. You do 1 plus count of root left, then you will actually do null arrow left. And whenever you do null arrow something, you get null pointer exception because null is nothing. When you use arrow operator, you are trying to extract something from R. And if R is null, the computer will say, hey, it's illegal. It's null pointer exception. So this thing is not applicable if R is null. So I would say that, hey, this thing is applicable only if R is non-null. But if R is null, think about R being null. So let's say there is an empty tree. There is an empty tree. There are no nodes in it. It means that its root would be null. So if the root is null, then the number of nodes would be 0. So in that case, you should return simply 0. So this is your base case. And this is your regular case, which I can call as your recurrence relation. So these two things you have to plug in your function and then call that function for the root of your entire tree, and then your job will be done. Does it make sense why this base case exists the way it is? Yes or no? Yeah. Okay, can we code it now? So let's say there is a function count. This count returns an integer denoting the number of nodes present in the tree, which is rooted at R. So you pass a node star R over here. And now the first thing you should always write is your base case termination condition. So you should say, hey, if R is null, so you can either write R equals to null, or you can just write not of R. So if R is null, return 0. Otherwise, you can just return this expression, which is intending to say 1 plus count of nodes in root left plus count of nodes in root right. That's it, job done. Make sense to all? Yes, no? Okay, now is there anyone here who struggles to understand the recursive codes, who maybe is not so very confident understanding how this code would work and all. If that is the case, I can draw a recursion tree diagram, helping you understand that how it sort of works. Yeah. Okay. Since it is the first question, I can do that. Let's take a look. Okay. It will make your life easy in all the upcoming questions. So let us understand. Okay. But do you guys understand how this is fundamentally correct? Forget about how the code would operate on it, but do you understand how this is fundamentally correct, this equation? Yes, no? Okay. So if you understand how this is fundamentally correct, just make a note of it on your piece of paper that no matter what tree question you have, you always have to think in terms of root, LST, RST. You always have to break your big tree into these three components and you will always be able to solve it. Okay. Now I'll just give you a glimpse of how this code would run. For that, I would need an input. Let's say you have a tree that looks like this. 2, 3, 4, 5, 6, and let's say 7. Okay, cool. This is your tree and you want to run this code on top of that tree. So you would first, let's say this is your main function here. From this main function, you would make a call to that tree for this node. So you would call count at that node, which is 2. I mean, you would not pass 2 here, you would pass the address of 2. If let's say the address of 2 is stored in R, you would pass R over here. So what will happen? You call count of 2. Now let's look at the code. This thing is not null. So this termination condition will not run. Rather, this thing will run. When it runs, then it means it will first make a call to this 3 because this 3 is root left. So you will call count of 3. And after that, you will call count of 4. Correct? Now, you might have learned how recursion works. The control comes from here to here. So now when you are at count of 3, this thing gets called for 3. Again, this condition is false. So you will come here. When you will come here, you will make a call to count of 3's left, which is 5. So you will call count of 5. And after that, you would also call count of 3 right, which is 6. Okay, before I draw further, is it clear so far, whatever I am drawing? Are you able to take some sense out of it? Yes, no? Okay. Now, from count of 3, you have come to count of 5, right? So you have come to count of 5. Again, this 5 is not null. So you will come here. You will return 1 plus, so you will call count of 5 left. What is 5 left? What do you see in 5 left? It's null. It's null, right? So you will call count of null. Correct? And after that, you would call count of 5 right. 5 right is also null. So you will call null here. So what has happened is that so far, computer knows about this much. So far, your computer has taken control from here to here, here to here, and then here to here. Now, at count of null, this condition will be true because the root is null. So you will return 0 from here. So you will return 0 from here. Similarly, at this count of null also, you will return 0 from here. Now, think when count of 5 was called, then you had returned 1 plus this thing plus that thing. Now this thing is 0. That thing is also 0. So count of 5 will return 1 plus 0 plus 0. So count of 5 will return 1 plus 0 plus 0, which is 1. And it makes sense to return 1. Why? Because I had told you the responsibility of this function is that whatever is the tree rooted at R, it should tell me how many nodes are present in that. So the tree rooted at 5 is this much, and the number of nodes present in this much is 1. That is the reason it is returning 1. This is how recursion works. The control goes from top to bottom, and the returns happen from bottom to top, and then they kind of, get consolidated as they move upwards. Is it making sense? I'll deep dive more on this, but are you guys understanding how things flow? Correct? Okay, so now you come at count of 3. Count of 5 was already done. So this count of 3 will call that count of 6 that I had written over here. Count of 6 again, according to this logic, will call count of 6 left, which is null, and count of 6 right, which is also null. So it will call count of null. Count of null. What would it return? At null, you always return 0. So you return a 0 and you return a 0. And now again, if you remember, at count of 6, you had promised to return 1 plus something plus something. Those two things are 0, 0. So you return 1 plus 0 plus 0, which is 1. Again, it makes sense. Because when you say count of 6, then the number of nodes present in this subtree is 1. And that is what it has done. So every children is doing their job. Like 5 is doing its job to say that, hey, I got one child within me. 6 is saying I got one child within me. And then this 3 is saying that I got 1 plus 1 plus 1 child, which is 3 children within me. So if you take a look at count of 3, you had said you will return 1 plus number of children in left and number of children in right. Number of children in left is 1, number of children in right is 1. So you'll return 1 plus 1 plus 1, which is 3. And again, it is right because here there are 3 nodes. Similarly, when count of 4 is called, you will first call count of 4 left, which is null. And then you will call count of 4 right, which is 7. At null, again, you will return 0. And at count of 7, again, you will make a call to count of 7 left and count of 7 right, which is count of null, count of null. You will return 0, you will return 0. And at this count of 7, you will return 1 plus 0, which is 1. And this count of 4 will again return 1 plus 0 plus 1, which is 2. And this count of 2 will return 1 plus 3 plus 2, which is 6. That's how things get returned. Does it give you enough clarity now, like how this piece of code runs on the tree? Yes or no? Right? So if you are clear with how recursion works, and if you can fundamentally write such kind of equations, then 90% of the job is done on trees. Okay, cool. If you have any questions, feel free to ask before I give you some other problem to solve. Okay, so let's take another question now. Now what I want you to do is I want you to count the number of leaves. How many leaves do you see in this tree? Leaf means nodes that do not have any children. There are 3 leaves in this tree. So can somebody come up with a similar sort of equation that we had written earlier for the count of leaves as well? What do you have to do? You have to break your entire big tree into a root and a left subtree and a right subtree. Okay, tell me one thing. The previous equation that we had written, that equation was count of leaves in the tree rooted at R is 1 plus count of leaves in R left plus count of nodes, not leaves, in R right. Will this equation hold true if I have to count the number of leaves also? Will it make sense? The answer is no, it will not make sense, because fundamentally here you are saying that, hey, the number of leaves in this is equals to 1 plus the number of leaves in this plus the number of leaves in that. No, wrong. Why you are counting 1 for this? This is not a leaf. If it has some children with it, how can it be a leaf? So this equation is not right. But if you omit this 1 from here, will now this equation be right to count the number of leaves? The answer is yes, because now you can say that the number of leaves in this entire tree can be thought of as number of leaves in left subtree plus the number of leaves in right subtree. As simple as that. Is that now making sense to all? Correct? Okay, cool. So now if I have to code it, let's go ahead. So let's say int count it takes the node. Okay, so I'll keep everything the same. I'll say if root is null. So if root is null, that means you are talking about a subtree which is empty. An empty tree has no nodes, so it has no leaves. So here I'll return 0. And otherwise, for the normal nodes, I'll return the count of leaves in its left subtree, and I'll add to it the count of nodes in the right subtree. Is this code correct according to you? Yes or no? Yeah. This code is not correct. Just think of it. What will it return when I run this piece of code on this input? See, I have already run another piece of code on this input. I want you guys to run now this new piece of code on this input. See what you get. Most of you are saying you will get 0. You will always get 0. Is that true? Okay, let's do some work. The way I have created this kind of diagram for the previous code, please create a new sort of diagram on the current code. Okay, see what will happen. Let's keep watching, everyone. I'll erase these things. Okay, see, the flow will be same. From count of 2, you will come to count of 3. From count of 3 to count of 5. From count of 5, you will call count of null. And at null, you are returning 0. You return 0. You return 0. Now, for the normal cases, you are just adding what you get from left and right. From left and right, you got 0. 0 plus 0 will be 0. That you will return. Similarly, from here, you will return 0 plus 0. And again, from here, you will return 0 plus 0. Similarly, from here also, you will just return 0, 0. You are just returning 0 plus 0 plus 0. So eventually, you will only return 0. If this is the code that you write. Is that making sense to everyone? That why you will only be returning 0 in this case? So this is very important to understand. So what to fix? What is the very, very fundamental mistake that we are doing over here? The very fundamental mistake that we are doing over here is we are never counting the leaves. We are just returning 0. We are never counting the leaves. This thing is fundamentally correct, but this has a base case. It has a base case for what? It has a base case for the nodes that are actually the leaves. Because when you touch upon a node which is actually a leaf, so I would say if R is a leaf, then you should return 1. Why you should return 1? Because yeah, it is a leaf. So if you are talking about the subtree rooted over here, there is only one node in it. So you should just return 1 from here, symbolizing that. Does it make sense to all? Yes or no? You know, these are the kind of cases that you have to handle. I told you at the beginning, when you write the code, you will have to handle some special scenarios. And most of the time they'll be happening for leaves or for the roots. Okay, now can you check whether a node is a leaf or not? It is very easy to check. So if this is R, you just have to check if R left is null and if R right is also null, then I can say it is a leaf and then I can return 1 in that scenario. So let me change it. I would say if R left is null and R right is also null, that means R is a leaf, and in the subtree rooted at leaf, there is only one leaf. So I'll return 1 from here. Now, is this code correct? It looks like it is correct, but it can still mess up with me. When will it mess up with me? Think about that. So let's take a look. Let's say you are at count of 4. At count of 4, you would make a call to count of null, correct? When you make a call to count of null, what you will do is here you will check for count, you will check for R arrow left. And because your R is null, you will end up getting a null pointer exception. So this code is not null safe. Not null safe means if the past value of R is null, this code can mess up. So you have to take additional handling of the case when your R becomes null. For that, you can add your first condition here. It will be same as the previous condition. If R is null, return 0. Theoretically, it is trying to say that if the subtree is empty, return 0, which is correct. So it will not lead to any wrong output, but what it does is it protects you from null pointer exception. So now this code is perfectly correct. If you make a call to null, you return 0 from here. And if you make a call to a node that is leaf, you return 1 from there. And now if you return the proper things, you will see it will work properly and it will be all right. So there are two termination conditions over here. First termination condition is when you touch a null, and second termination condition is when you actually touch a node that is a leaf. Is it making sense, all the different nuances which we encountered while writing this code? Yes, no? Yeah. Just in case if you want me to repeat anything, you'll have to exactly tell me what you want me to repeat. This entire thing cannot be repeated, however. Yeah. Any doubts so far? Yes, no? Last point, I do not remember what was the last point. You tell me like what exactly conceptually what you did not understand. That will be better for for me to talk about. Like, anyways, I'll tell you this thing again. Like, do you realize that if you do not have this condition, you can run into null pointer errors? You realize that? Because sometimes you might make a call for null, and if you do not have this line, you will do null arrow left, that will give you null pointer exception. So you have this piece of code that if by accident you make a call to null, that means you're talking about an empty tree. An empty tree has no leaves, so you return 0. So now because you have this condition, whenever R is null, this condition will run. The code will not flow to this condition. It's as simple as that. I hope you must have understood by now. Yeah. Okay, good. Cool. Now let's talk about the time complexity of this code. This code and also the last code that was counting the number of nodes. Any guesses? It'll be order of n. Good. Why it'll be order of n? Because whenever you have a recursive code, you just have to see that how many times this code is touching a node. Now here I can clearly see we are touching a node only once. And whenever we are touching a node, we are doing very trivial number of operations. We are just adding two integers that have been returned to us. So adding two integers is constant time operation. So I can say at every node, I am doing constant time operation, which is order 1 operation. Now, because there are n nodes, so n into order 1 can be written as order n. So this code and the last code, that was doing two additions. It was doing 1 plus count of left plus count of right. There was also two additions is also constant time, order 1 you can write it. So I can say the time complexity is going to be order of n. Is it making sense to each one here? Yes, no? And how about the space complexity? So let me see how much you have understood recursion. Is there some extra space we are using in this particular code? Yes or no? First answer that. Recursive stack. Yes or no? Recursion internally creates a recursive stack. For example, when you are at count of 2, you call count of 3, you call count of 5. So what happens is this entire thing that you have goes in a recursive stack. So this function has on its top this function, and this function has on its top this function. So it means that if, let's say, this tree had a height of this much, then the largest recursive stack that would have got created would have been of this much. And what is this? This kind of thing is also called as height of the tree. This is height of the tree, how longer the tree is or how high the tree is. So I can say that, hey, the space complexity is definitely there because recursion internally maintains a recursive stack, and the height of that recursive stack will depend upon the height of the tree. So your extra space is going to be order of h. Is that clear? Yes or no? That how it is order of h. What can be the maximum value of h if there are n nodes in the tree? What can be the maximum value of h? So I just told you it can be n if the tree is completely skewed. Imagine all the nodes lying like that. It will be a skewed tree. In that case, your extra space would also be order of n. Yeah. Is it most of the case in case of tree space complexity? I mean, that's not the right kind of thing to have in your brain. But yeah, you can say that most of the recursive code that you will write there, the recursive tree will be a function of the height. Now, what function that you have to figure out? Here it is order of h. Sometimes it can be order h square also. That's totally dependent upon the algorithm which you write. Clear? So let's move on to some other questions. Okay, we'll take a very popular interview question, very frequently asked in the first round or phone screening rounds. So you have been given a tree, let's say something like that. You have to convert this tree into its mirror image. Mirror image. Okay, what kind of image does a mirror create? What is the property of, if you stand in front of a mirror, what does it do to you? Lateral inversion, that is right. Lateral inversion means that if you have a mirror, whatever appears in left, that appears in right, and whatever appears in right, that appears in left. And now this left-right combo is very much in sync with whatever we have learned, because we know that, hey, a tree is composed of a left subtree and a right subtree. So it looks like I have to swap them. It kind of looks like that, right? So if I have a mirror here, of course, this 2 will remain 2, but this 5 thing will come here, and this 3 thing will go there. So basically, the left and the right children are going to get swapped. But this swapping, will it only happen for the children of 2, or will it happen for all the nodes? It'll happen for all the nodes, right? The same thing will happen for 5 also. Its left child was null and right child was 4. So now what will happen is that now the left child will be 4 and the right child will be null. So you can see this 4 is here and this null is there. And for this 3 again, the left and right, which was 6, 7, will be changed to 7, 6. So this is a mirror image of that. So how many of you can write a piece of code that that kind of does this thing on a tree? Mirror image is a tree. The easiest possible code that you can write, all that you have to do is you make a function call to, let's say, R. And when you are at R, you don't have to do anything to this R. You just have to swap R left with R right. And you know how to swap 2 items using a temporary variable. So you can have a temporary variable that swaps these 2 children. And then you have to recursively make a call on the left subtree and right subtree also. You have to make that call. Why? Because you have to perform this swapping for all the nodes, right? So let's say we have a function called as toMirrorImage. toMirrorImage takes node star R, which is root of a subtree, and it is void. It does not return anything. All that it does is it structurally changes the tree. So tell me how to write the code. What should be my first line over here? Or in general, what should be my first line in any recursive code that we write? Base case. So what should be the base case? Yeah. See, whenever you are traversing a tree from top to bottom means when you are at root, you are making call to root left and root right. So you're coming down. So when you're coming down, you will eventually come to null. So when you come to null and then you try to do null arrow right, null arrow left, very bad. So you don't have to do anything when you touch null. So you would say if R is null, don't do anything, just exit, just return. Okay. Otherwise, the first logical step that you want to do is you want to swap the children. And the next logical step that you want to do is you want to go down, or you want to make recursive calls to the left and right. So this first logical step is very easy. You can have a node star temp, because you want to swap this with that. So maybe in temp, you can temporarily store r left. And then what you can do is r left equals to r right. And now in this r right, you can accommodate temp. So when you do this sort of thing, what has happened is after just this much offline, the left child of 2 has become 5. So now the situation would be the left child of 2 is 5 and the right child of 2 is 3. But you do not want just this much, you want that much. So it is important to make a call here as well as here. So after this much, you need to do to mirror image. You need to make this call for root left and to mirror image root right. The responsibility of this call is to convert this into mirror image. The responsibility of this call is to convert this into mirror image. These calls will not tamper whatever you have done above, right? They'll just do their job and everything will be done. So again, classic case of do something at the root and then delegate the calls for left and right. Does it make sense? How many of you understood this particular code? Yes or no? Super easy, correct? Okay, let's move on. Okay, we'll solve a first good enough question on tree. So there is a well-known English word called as symmetric. Okay, like an array can be symmetric, isn't it? So what I mean by symmetric array is, let's say you have 3, 2, 1, 2, 1. This is a symmetric array according to me, because this is the line of symmetry. You have 2, 2, you have 1, 1. Correct? Similarly, you can have a symmetric tree also. Can you imagine how a symmetric tree would look like? Can you imagine it in your head? Force yourself to imagine. Okay, let's take a look. A symmetric tree would be something like this. So let's say you have 10, and then here you have 9, 1, 12, 6, 5. Here you will have 9. Here you will have 12. Here you will have 5, 6, 1. This can be regarded as my line of symmetry. Tell me, does it look symmetric to you or not? Yes or no? Yeah. Okay, so the question is very simple. The question is that you have been given root of a tree. You have been given root of a random binary tree. And you have to check whether that tree is symmetric or not. If it is symmetric, you have to return true. Otherwise, you have to return false. So you have to write a function that returns Boolean. And the name of that function could be is symmetric. And what it takes in input is the root of the tree. So you have to fill in the blanks here and make this function return true or false depending upon whether the tree rooted at R is symmetric or not. Is the question making sense to all? Yes or no? Yeah. Okay. So, before we move on to the solutioning part, see, one thing is very, very true. So before your fingers work on the keyboard, your brain should work. So when you are thinking, you think fundamentally, you do not think in terms of code. Think fundamentally that what is the property of a symmetric tree. Once you are clear with the property, you can convert that property into a recursive equation and then you can code it. Correct? So what is the property? Let's first talk about the property of a symmetric tree. Few of you have already talked about that. R left equals to R right. Okay. But what is your R here? When you say R left equals to R right. So most of you are saying R left equals to R right. This is extremely misguiding for me, because if this is my R left is 1 and R right is 12 and they are not same. So is it correct to say that R left is equals to R right for different values of R? This is not right. Yeah, but what many of you are saying, that is absolutely right. So many of you are saying that the left subtree, which is this, and right subtree, which is this, both of them are mirror images of each other. Left subtree is a mirror image of right, right subtree is a mirror image of left. So if that is true for any tree, then that tree will be symmetric. Does it make sense? Do you guys agree with this? Correct. Even in array also, this part was mirror image of that. If you put 1, 2, 3 in front of mirror, you will get 3, 2, 1. So if the left part and the right part are mirror images, my job is done. So if, let's say I have a separate function called as R mirror image, what it does is it takes two subtrees. So let's say the root of the first subtree is R1 and second is R2, and it returns whether the subtrees rooted at R1 and R2 are mirror image or not, then my job will be done. So if you can write this, then you can just call this function from here. You can just call R mirror image for the left and the right subtrees, which is for R left and R right. And if it returns true, you want to return true. If it returns false, you want to return false. So now all that you have to do is you have to fill in the blanks here, not there. So how many of you can write the piece of code over there? How can I check whether the two trees are mirror images of one another or not? Okay, so again, you have to think in terms of root, left subtree, and right subtree. Again, the fundamentals remain the same. Let's take a look at the board. This is quite important to understand. See, if you want the tree rooted at R1 to be mirror image of the tree rooted at R2, the first thing which is important is that R1 and R2 both should have the same value. This has to hold, because the moment R1 and R2 have different values, there itself you can say that the tree is not symmetric, no need to go down. Is it right what I'm saying? Yes or no? So that is the first thing which should be true, that R1 data should be equals to R2 data. Correct? But only this much is not enough. Certain other things also have to be true. And that means that the right of it should be mirror image of the left of it. So the right subtree of R1 and the left subtree of R2 should be each other's mirror images. Do you see that? Yes or no? Similarly, the left subtree of this and the right subtree of this should be mirror images. So this should be mirror image of that, and this should be mirror image of that. Now it looks like in order to check whether this is mirror image of that or not, I just need to check whether this is mirror image of that and this is mirror image of that. So this problem is again recursive. To solve bigger, you have to first solve for smaller. Do you connect with me on this? Yes or no? Right? So what I would want is that the tree rooted over here should be mirror image of the tree rooted over here. So now this is the function that checks whether the two subtrees are mirror image or not. So I can recursively call this function R mirror image for the tree rooted over here, which is R1, right? And along with it, I can call R2 left. Correct? And also I want to ensure that this is the mirror image of that. So I need to call R mirror image of R1 left in association with R2 right. Now, for these two things to be mirror images of one another, all these three conditions have to be true. When you want all the three conditions, C1, C2, C3 to be true, what operators do you use in between them? You use AND operator, logical AND operator. So you want this to be true, and that to be true, and that to be true. So you would return this expression. If this expression is true, that means the tree rooted at R1 and the tree rooted at R2 are both mirror images, otherwise not. Is it clear what is the intent of this expression? Yes, no? Okay, any edge cases? Any edge cases that we will have over here? So I can just transport it from here to here. Imagine it is written here only. Now there have to be certain edge cases that you need to take care about. Leaves is still okay, because let's say if you are here and if you are here, you will still check whether this value is same as that or not. And then you would want to check whether null is mirror image of null or not. And this null is mirror image of that null or not. That is still okay. The problem might arise when both of them are nulls, because see here what you are doing is you're directly using arrow operator. Now you cannot use arrow operator on null. So sometimes it might happen that this is null and that is non-null. And sometimes it can be vice versa, that this is non-null and that is null. And sometimes it can be that both of them are null. Now, the point is, even if one of them is null, this thing will throw null pointer exception. So I need to take care of nulls separately. How to take care of nulls? So I can say, if R1 is null, that means R1 is empty. And if R2 is non-null, that means R2 is something like that. Can an empty tree ever be a mirror image of non-empty tree? Is that ever possible? The answer is no. And the vice versa would also not be true. But if both of them are null, then I can safely say that, yeah, they are mirror images. So only if both of them are null, then I would return true. And if one of them is null and the other is non-null, then I would return false. So how I can code it, I can say if R1 is null together with R2, if both of them are null, just return true. But if R1 is null or R2 is null, then return false. And I have intentionally written this condition after this condition, because if this condition is not true, that means both of them are not null together. And if this condition is true, that means either this is null and that is non-null, or vice versa. In that case, I'll return false. So this is a termination condition, that is another termination condition, and this is our recurrence relation. That's it. Does it make sense? Yes or no? How many of you are clear with the termination condition? Yeah. Okay, cool. Did not get the third condition at last. So if you, what is the third condition? You mean this? If you got this, then you should be able to get this also. You understand when two trees are mirror images? The two trees are mirror images if the value present in the nodes are same, the value present in the roots are same, which is what is written here, and the right subtree of R1 is mirror image of the left subtree of R2. Similarly, the left subtree of R1 should be mirror image of the right subtree of R2. That is what is written over here. This was the most basic thing to understand. Yeah. Termination condition, again, like you yourself think what will happen if R1 or R2 is null. If R1 or R2 is null, you will get a null pointer exception here. So you need to take care of them over here. Now think, what is the meaning of R1 being null? R1 denotes the root of a subtree. So if the root of a subtree is null, that means that subtree is empty. So if you have an empty subtree and another subtree which is non-empty, can they ever be mirror images of one another? No. Only if both the subtrees are null, which means only if both the subtrees are empty, then they can be regarded as mirror images. That is what I have written. If R1 is null in association with R2, return true. Otherwise, if one of them is null and the other is non-null, then return false. Makes sense? Now, how many of you are able to understand how these relations are being written and how termination conditions are being thought of? That is the most basic step that you should be learning in first class of trees. And that is what you should walk on also. So whenever you are solving on a tree, don't do random things. Okay, don't just do some trial and error and get the code working. See whether you are able to think of recurrence relation and termination conditions, because these are the only two things, then the job is done. Okay. So this is the code that I needed to write, and this function has a dependency on that function, which does its job. Now I have another basic question from you. What if R itself is null? Which is, what if the tree which you have to check is symmetric or not, that tree itself is empty? If that tree itself is not empty, will you not get a null pointer exception over here? Yes or no? You will get a null pointer exception. So again, you need to handle that separately over here. So you can say if R itself is empty, is null, then return true, because an empty tree by default is symmetric. It has nothing in it. Does that make sense to all? Yes or no? How to think of termination condition? As I had said at the beginning, think of termination condition at the level of leaves and the nulls. When you are reaching leaves and when you are reaching nulls. So whenever you see a code that has arrow operator in it, then think whether R1, R2 can be null or not. If they can be null, how to handle them. That is the most basic step that you can take. Yeah. Okay, anyone having any other question based on what we learned so far? Okay, cool. So we just had a very basic class on trees. So munch on the ideas that I have discussed so far. Okay, how trees work on. Trees do not work on call stack. It's recursion that creates call stack. Okay, so please revisit recursion. I believe it would have been explained like how, I think there is a video also that I have created on YouTube. You can maybe refer to that. But we have extensively talked about how these call stacks work and why do they even exist in the world of recursion. Okay. Cool. So that will be it for today. Tomorrow when we meet, then we will be solving some more questions on trees. We will continue with some, I would say, medium level or harder level questions on trees. And by tonight, make sure you code these questions and practice them as far as possible. Yeah. Okay, that will be it for today. Let's meet again tomorrow. So bye everyone and have a good day. We'll share some problems, okay? Don't worry.